Hello everyone, welcome back to ch205. In this video, I'll be talking about an example of how to calculate the numerical derivatives using first or second order approximation. And in particular, we're going to use a table on page 83 of the textbook. So the problem is as follows. We want to calculate the heat capacity at constant pressure, which is given by the derivative of enthalpy with respect to temperature. So if enthalpy is given in this table, like this is H, this is temperature, and we want to calculate the derivative of enthalpy with respect to temperature at a constant pressure. So we need to use numerical derivatives because we don't know the analytical form for enthalpy. Okay? All right. So in part A of this problem, we're going to use final difference to calculate the heat capacity of carbon dioxide at any given temperature. And we have to make sure that we use endpoint formulas for the first and last entries. All right. So the way we go about doing this is the following. So this is the table exactly like in the textbook. If I increase the font to 14. Right, so this is the temperature, this is enthalpy, and the unit is kilojoules per mole, right? Okay, so we're gonna carry out the derivative. For the first cell right here, we have to use endpoint. Why? Because, well, what are the options? The options are, we can use forward difference, forward because if I want to calculate derivative at this point, and the only points I have access to are the second point and third point, right? If I look at the temperature as an axis, along this axis, the temperature is going up, right? So if I'm sitting at this point and I want to calculate the derivative, I cannot use backward difference because for backward difference, you need to know the point before this, but there's no point before this in the table. For central difference, we also need to know a point before this and after this. Well, we have access to the point after this, but we don't have any information about the point below 100 degrees, right? So if you go back to page 83, just to remind you that, so for backward difference, if you want to calculate the, let's say, derivative at temperature 100, you need to know the value of the enthalpy at temperature, let's say 100 minus delta x. And in our case, delta x is the difference between two successive temperatures, which is 50 degrees Celsius, right? So that means for backward difference, we need to know the temperature at 50 degrees. We need to know the enthalpy at 50 degrees, which we don't have. And if you go to second order, if you go to central difference, to calculate the first derivative of enthalpy with respect to temperature, then we need to know the value of the enthalpy at, again, T equal 50, right? We don't have that, so that's why we cannot use central difference, we cannot use backward difference, and all we can use is forward difference. So we're going to use forward difference with first order approximation, which is this one. And for this, or actually we can use this or that, yeah, it doesn't, well, either would be fine. So for forward difference, we need to know the temperature at 150 and 200. And same thing here, if you want to calculate the first derivative at 100, we need to know the enthalpy at 150, like 1 point away from the original point we want to calculate the derivative with the separation of delta x. In our case, it's going to be delta t. All right. So apparently I'm using here second order approximation because there are three terms, minus 3 times 2 points ahead of the current point, and then 4 times the point ahead of that, and then minus the temperature at the current point, right? So, and that is exactly the equation for a forward difference with second order approximation, which is this, right? Minus 3 times the current enthalpy plus 4 times the next enthalpy and minus enthalpy at next point. And then divide by 2 del x. So here we have to divide by 2 del x, which is 2 times 50, right? The difference is 50. 2 times 50 is 100. All right, so that is the first point. That is the end point. Let's look at the last point. Here we have to use also the end point because we do not know the temperature at 850. So any formula that uses enthalpy at 850 cannot be used because we don't have that information. When we go back here, then the same issue arises. For central difference at the last point, we need to know the temperature or the enthalpy at 850. We don't have that, so we cannot use central difference. If we want to use now this time forward difference to calculate the heat capacity at 800, we need to know the enthalpy at 800. Okay, that's fine, we have it. We have to know the enthalpy at 850, we don't have it. We need to know the enthalpy at 900. We don't have that one either. So this equation cannot be used. We're going to use this one, the backward difference, because we know the enthalpy at 800, we know the enthalpy at 750, and we know the enthalpy at 700. Right? This is I minus 1, I minus 2. That means 1 point before 800, 2 points before 800. Okay? So we're going to use this equation for the last point, and that's what I have here. Minus 3 times the current cell. I'm sorry, 3 times the current cell minus 4 times the previous cell, and then plus the cell with distance of 2 delta x from the current point. Okay, so and that's exactly this equation, like 3 minus 4 plus 1, and that's exactly here, 3 minus 4 plus 1 divided by 2 del x, right? And del x is 50, 2 del x is 100. All right, so that's the end point. Now for all other points in between, we're going to use central difference. I'll just show you one of them, and then the rest would be the same as I had here, central difference. To calculate the enthalpy at this point, we get the point after that, which is the blue cell, minus the point before that, which is the green cell, divided by 2 del x. That's going to be the first order derivative of enthalpy with respect to temperature, which is the heat capacity. All right, so that's the central difference for this point. And for all other points, you do the same thing. You get the enthalpy at the next point, minus the enthalpy at the previous point, and then divide by 2 del x. All right. And that was, let's see, central difference. This is it. So we did central difference for the intermediate points, right? The point ahead of the current point, the point before the current point divided by 2 del x. Okay? All right, so we use central difference for other points because we have both the value of enthalpy before and after. Okay, so this is how we can calculate the enthalpy, the heat capacity for all points. Then we get the average of all these, assuming that the enthalpy, should not change with temperature. Well, enthalpy actually changes with temperature. The heat capacity, which is the derivative of that, is supposed not to change with the temperature. So we get average of all these, which is about 0.04. All right, so let's look at part B of that problem. So in part B, we need to graph the enthalpy of the data and then fit a curve and then compare that with part A, compare the heat capacity from the curve that we just fit. Okay, so to do that, we first plot enthalpy against temperature. So that's what I did. These dots are the enthalpy against the temperature, which means second column against the first column here. Okay, and to do the fit, what you do is you right-click on your data. So let me get rid of the line. Let's see if we can click on that. Yes. All right, so this is the data I have. It's the raw data. Then I click on my on one of the points, and then right-click on my mouse, go to Add Trend Lines, and then I pick Linear Function. Then I hit OK, and then it draws this line for me. And to get the equation for this line, again, you right-click on the point. Then you go to format trend line again. Here you click on options, and then we say show or display equation on chart. You're just going to click that and OK. Then you see that the equation shows up here, and if it's small, you can go to home and increase the font to maybe 12 or 14. All right, so this is the slope. So what is y? Y is this guy, which is enthalpy, and x is temperature. So this is saying that enthalpy varies linearly with temperature. So forget about the intercept for now. If I take derivative of y with respect to x, means I'm taking derivative of enthalpy with respect to temperature. So this is slope supposed to be the enthalpy we calculated numerically here. So if you want to compare the solution of part B and part A, I'm going to copy this, just the slope right here. This is the slope from the curve fit. This is the average we got from part A, and these should be very close, which I think it is. So I think we are fine, almost on the right track. Okay, so that was part B. And for part C, we have to compare with the NIST data from exercise 4.2. So CP, the heat capacity, actually is given to us from the NIST table. This is the NIST table, temperature, and this is the heat capacity. So I copy the heat capacity to this table right here. This is the heat capacity from NIST, right? And make sure the unit actually is right. So the unit as of now is joule per mole per Kelvin. There's an extra I here. Get rid of it. Okay, so this is joule per mole per Kelvin. Joule per mole. I think this should, yes, this is per joule, well, joule per mole per Kelvin. So Kelvin is downstairs. All right, I want to compare, and these are at the same temperature, right? So from 100 to 800, same as here, from 100 to 800. And I have like one-to-one correspondence. All right, so I want to compare this one with the one I just calculated numerically using the numerical derivative. For what difference? Well, this guy is kilojoule per mole per Kelvin. And this one is joule. So to convert kilojoule to joule, or joule to kilojoule, to convert joule to kilojoule, then I have to divide this by 1,000. And I did it right here. So this column is this column divided by 1,000. So I have to compare this cell, make it yellow, and this cell, get yellow too. And when you compare, they're almost close. And you can go all the way down and compare one cell at a time, and you can actually find the error. So how we can find the error for every cell? Well, the absolute value of this cell minus the original cell here we calculate numerically, right? We find the difference, we get the absolute value, and we divide by the original value, which is the the more exact, which is coming from NIST data. So to calculate the error, I get the numerical derivative minus the NIST data. I'm sorry, this is the NIST data. So yes, K3 is the NIST data. So NIST data minus numerical derivative divided by NIST, because we're assuming NIST is more accurate than our derivative. So that's why we based the calculation on the NIST data. So NIST data is downstairs, and the difference between the NIST and derivative is upstairs with the absolute value, because we don't care about the sign. And that gives us the error. We multiply by 100% or 100. That gives us the percentage of the error. So we can drag this guy down, and that's going to be the percentage of the error. For the first point, we have a bit large error. The other ones are a bit small. This guy has a large error as well as the last one. So the last ones usually give more error because we're using forward difference, and forward difference is first order. Remember that. Well, actually we use the second order, but central difference is more symmetric and more accurate. That's what we can say for now. So I think that's the part C. All right. So thank you so much for watching. Stay tuned for the next example, numerical derivative or numerical integration.